Hello, and thanks for joining me today as we continue our discussion on gases and energy. We talk today about states of matter and phase changes. So today we're going to talk about the kinetic molecular theory. We'll be able to explain the three parts related to gases. We're going to look at the differences between solids, liquids, and gases in terms of molecular movement. You'll be able to identify starting and ending phases during a given phase change. You'll be able to distinguish between heat of fusion and heat of vaporization. You'll understand what is happening on a heating cooling chart or heating cooling graph, and you'll be able to perform combined energy calculations that involve a phase change. So let's get started. First off, your kinetic molecular theory is the idea that all matter is made of particles that are in constant motion. So when we talk about gases, we assume that gases are small hard spheres with insignificant volume. We assume that the motion of the particles in a gas is rapid, constant, and random, meaning they travel in a straight line and ricochet off walls without changing directions, without added spins and things like that. So the random motion. And all collisions are perfectly elastic, meaning they don't lose any energy when they collide with each other. Okay, so those are your three assumptions about gases. When we talk states of matter, we have solids, liquids, and gases. Solids have a definite shape and a definite volume. The particles are stuck together, and there's a strong force of attraction between them, so they can't move. They're stuck in place. They just vibrate. Liquids have a definite volume, but not a definite shape. They take the shape of their container. Particles move freely in random directions, but they must always be touching one another. So they're still close and have a strong attraction to sustain that volume, but they're allowed to flow past each other. And then your gases have no definite shape nor volume. Gases are free-flowing. They move extremely quick. Their attraction is no longer there, so the particles can escape and move wherever they would like to within the container. When we talk about state changes, so you're familiar with a lot of these, but converting from one state to another, we have freezing and or melting. So freezing goes from a solid to a liquid. Melting goes from a liquid to a solid. So those are your two changes between solid and liquid states. Evaporation and condensation. A liquid going to a gas is evaporation. Condensation is a gas becoming a liquid. And the last two, these two you may have heard, maybe not. Sublimation is going directly from a solid to a gas. For example, carbon dioxide, dry ice. When you put water on it, it creates a fog. That's your solid going directly to a gas. And then deposition is the opposite of that. Deposition goes from a gas to a solid in the case of snow. Water vapor becomes solid water in the form of snow. Moving on. Some different terms that go along with these. We have a melting point, we have a freezing point. So your melting point is the temperature and pressure at which particles separate and move in random patterns. So you went from a block-like structure where particles are all touching to one where they are now allowed to flow past one another, and they don't have to be in this exact same order. So we can have motion there. They can slide past one another. Freezing point is the opposite. So when I go from this flowing state to a structured fixed solid state. So melting point is temperature at which you go from a solid to a liquid. Freezing point, you go from a liquid to a solid. Again, terms I think you've heard before. One you probably haven't is heat of fusion. This is the energy needed to go from either a solid to a liquid or a liquid to a solid. So this is the energy associated with these two phase changes. In the case of water, your heat of fusion is 80 calories per gram. So for water to freeze, it has to lose 80 calories per gram in order to form ice. For ice, it has to gain 80 calories per gram in order to form water, liquid water. This graph is showing you your phase changes. If you can understand this graph, this unit makes a whole lot of sense. So the temperature we have on the left in degrees Celsius, the bottom we have energy or heat. So from negative 10 to 0 degrees, we are increasing in temperature, we're increasing in heat. But this is a solid state, this is ice. So this all indicates ice. Once I get to 0, you will notice a horizontal line. This horizontal line indicates that heat is still being added. I'm still gaining energy, but my temperature is not going up. because that temperature, that energy is being used to break those bonds between water molecules that's holding them together as ice. So here you have a water and ice combo. After all the ice is melted, you'll start to see an increase in temperature again. And this goes from 0 to 100 because 0 is the freezing point and 100 is the boiling point. So this is all liquid water. We are gaining energy. We are increasing in temperature as well. That makes sense. They go together. Here, we get to this point. At 100 degrees Celsius, we have a large increase in energy. But we didn't increase our temperature at all. This is the point at which your liquid water molecules have to break bonds between each other and become water vapor, become gaseous water. This takes a lot of energy, takes a lot of time. This is a very big horizontal line because of that situation. And then after all the water is evaporated, your steam is allowed to heat up, and your energy is added, your steam heats up. So it keeps flowing there. But if you can understand that my diagonal lines, my lines that have a slope that's not 0, indicate a singular phase of matter. So if this bottom one is a solid, this is a liquid, this is a gas. And at these horizontal lines, I'm having a phase change. So I'm either melting or I'm either condensing or I'm evaporating, depending on which way I'm going. And down here, I'm either melting or freezing, depending on which way I'm going, if I'm gaining or losing energy. But these graphs are really important to be able to understand. And now we have to do some calculations with it. So ice cubes at 0 degrees Celsius with a mass of 26 grams are added to a soft drink. How much heat and calories will be absorbed to completely melt the ice at 0 degrees Celsius? So the ice cubes are at 0, so we're at that first part of that horizontal line here. So they're at 0. I want to know how much energy, how much heat will be absorbed to melt the ice here. So how do I get across that phase and melt all my ice cubes? So for this, we know that our heat of fusion, I'll call it H sub F, is 80 calories per gram. And I know that I have 26 grams of water. So if I multiply these two, oops, I should not write that there because I just wrote heat of fusion. If I take my 80 calories per gram and I multiply my 26 grams, I get an answer of 2,080. Oops, I don't need. Maybe I do. I get an answer of 2,080. Put my comma in the wrong place. Calories, because I have grams on top and grams on bottom, which are going to cancel out. So 2,080 calories will be absorbed to melt the ice. What happens to the temperature of my drink at this, when this is happening? Is my temperature going to warm up or cool down? And the answer is no. Nothing's going to happen. Your temperature stays the same. Okay, so what's happening during this time is energy is being used to break bonds, not to heat the substance. So we're just breaking chemical bonds. All right, and then in the bottom, I give you this example. You can practice, try this one on your own. So try this one on your own. Notice you're going to kilojoules. So again, you have to convert calories, and then remember there are 4.184 joules equals 1 calorie. So then you can convert that and go to kilojoules. So if I place 120 grams of water in an ice cube tray in the freezer, how many kilojoules must be removed for ice cubes to form? So work through that. When you hit the next button, you'll get your answer. Your answer here should be 40.2 kilojoules or 40,200 regular joules. And so those are your answers there. Moving forward, so we did freezing and melting. On the other side, we have boiling point. This is the point at which all your particles in a liquid have enough energy to change from a liquid to a gas. This is when your water boils and becomes water vapor. To do this, instead of heat of fusion, we have what's called the heat of vaporization, which is the energy needed to vaporize 1 gram of liquid. This is 540 calories per gram for water. So the question comes, how does heat of vaporization and heat of fusion compare? Which one's bigger? Well, in this case, we know the heat of vaporization is bigger because heat of fusion was only 80 calories per gram. Why would this be bigger? If you think about the bonds between molecules, for ice to become water, we have ice stuck together like so. And so these just have to be able to start to slide. So they're still attracted, they're just not stuck in place. To become water vapor, I have to be able to take one of these molecules and completely remove it from the others. So it becomes its own separate molecule. It's not attracted to any other water molecule. So it takes more energy to do that than it does to just slide past one another. All right, let's do some practice. In a sauna, 150 grams of water is converted to steam. How many kilocalories of heat are needed to do this? So to do this, let's look at, here we have 150 grams of water converted to steam at 100 degrees Celsius. So I know that I have 150 grams at 100 degrees Celsius. My heat of vaporization, we talked, was 540 calories per gram. So if I multiply these two, my grams cancel out, and I get 150 times 540. If I do this correctly, I should get an answer of 81,000 calories, and I'm looking for kilocalories here, so this is going to be 81 kilocalories. I'll let you try the bottom one. When steam from a pan of boiling water reaches a cool window, it condenses. How much heat in kilocalories is released when 25 grams of steam condense at 100 degrees Celsius? So again, we're changing phases here. And so use that same equation, same calculation, and see if you can get your answer. I'll give it to you on the next slide, so pause this if you're going to work through that. Okay, and your answer here should be 13.5 kilocalories. Again, we had 81 for the last question. All right, again, one more time, we're going to look at this heating cooling curve. So here we have a solid. We either melt or freeze to become a liquid. So here's our phase change, which is a horizontal line. I have a liquid here, so I'm heating it up from going this way. If I'm coming down, I'm cooling it, so I'm losing energy. Here's my vaporization condensation point, and then I have a gas. So again, really important we can read and understand what that graph is indicating. All right, we have one last piece. This is our combined energy calculation. So this is calculate energy through a phase change. Either add energy to change temperature or add to change phases. So for example, we're going to calculate the calories needed to convert 15 grams of water at 25 degrees Celsius to steam at 100 degrees Celsius. We're going to have to use both the specific heat of liquid water, which is 1 calorie per gram, and the heat of vaporization, which is 540 calories per gram. We're looking for total calories here. So I'm going to flip to the next slide, or I have some room to work out our problem. So we're going from 15 grams of water at 25 degrees Celsius to steam at 100. So I need my, my water is going to heat up. We're going to have two calculations here. Water heats up. I'm going to use my Q equals MC delta T. I know that Q is what I'm looking for. So M is 15.0 grams. C, my specific heat of water in calories, is 1.0 calories per gram degree Celsius. And I know that I have to go from 100 to 25. So 100 minus 25, 25 to 100, I guess, which would be 75. So if I take 15 times 75 times 1, I'm going to get a Q value here of 1,125. Okay, now I'm converting this to steam. So then I need to know I have a phase change, which is going to include my heat of vaporization. So I have 15 grams of water, and it takes 540 calories to convert 1 gram of water into steam. So if I take 15 times 540, I should get 8,000, Q equals 8,100 calories. And then I can add these two together. So 8,100 plus 1,125, and I get Q being equal to 9,225 calories. Now, if I look here, I have 3 significant digits. So if you want to be specific and picky, Q equals 9,230 calories. Okay? So that's how we do those kinds of questions. Here's one for you to practice. So I want to know how many calories are released when 25 grams of steam condenses at 100 degrees Celsius, cools to 0 degrees Celsius, and then freezes. So to do this, you're going to need your heat of vaporization, which is 540 calories per gram. You're going to need your specific heat, which is 1 calorie per gram degrees Celsius, and your heat of fusion, which is 80 calories per gram. Pause this screen, give this one a shot, and I will give you the answer on the next page. Oops. All right, so there we go. Your answer should be 18,000 calories. If you do this all correctly, you should have a amount of energy needed to condense the steam, energy needed to cool the water, and energy needed to freeze that same amount of water. Should come out to 18,000 calories. All right, here are some review questions. So first page, pause this screen, answer these questions. Make sure you can tell me which phase changes are happening in the first one. How does sweating during heavy exercise cool the body on the second one? And then calculate the heat change at 100 degrees Celsius in each of the following problems. Indicate whether heat is absorbed or released in those situations. Question set number 2. I want you to draw a heating curve for a sample of ice that goes from negative 20 to 140 degrees Celsius. Indicate whether it's a solid, where it's a liquid, where it's a gas, along with melting points and boiling points. So if you can do that, you understand your graphs will be in good shape. And then your last set of questions. A bag contains 250 grams of ice at 0 degrees Celsius. It's placed on a burner on a patient's hand. When the bag was removed, the ice had melted and the liquid water had come to a temperature of 24 degrees Celsius. How many kilocalories of heat were absorbed by the ice and cool water? How many kilojoules is that? So there's practice at your conversions. Give these a shot. I look forward to working with you more as we continue this unit. And thank you very much. Have a great day.